Hi, my name is Philip Davis. I'm a research programmer at the Rutgers Discovery Informatics Institute. Today, I will be talking about the intersection of scientific computing with high-performance computing. In recent decades, advances in computing have changed many aspects of our lives. Computers have changed the way we work, learn, and relate with each other in many ways. Science is no exception. Computers have become important tools for discovery in virtually every field of research. Many important advances are being brought about or accelerated by the use of computers. For example, oceanographers are able to learn about the undersea environment with unprecedented clarity, thanks to data made available in near real time by the Open Oceans Initiative. Physicists are learning how to perform controlled nuclear fusion by studying simulations of phenomena that occur too quickly to be observed by direct experimentation. And quite recently, astronomers have been able to capture an image of a black hole, a task which would have been difficult or impossible without cutting-edge telescopy data analysis. The recognition of the potential computers hold to assist in scientific exploration has led to the rise of the field of scientific computing. This field combines the efforts of experts in many different disciplines, including computer scientists, electrical engineers, mathematicians, statisticians, and many others in order to develop and improve the hardware and software used for scientific computing. Many results can be obtained using conventional computing resources such as a scientist's laptop or cloud computing. However, the desire to learn about larger and more complex systems has led practitioners of scientific computing to develop high-performance scientific computing resources. These resources include supercomputers for performing simulation and data analysis at enormous scale, such as Summit at Oak Ridge National Lab, as well as data-enabled scientific instruments such as the Square Kilometer Array, an enormous radio telescope that will produce gigabytes of data per second when operational, requiring its own dedicated supercomputer to sort through this data in real time. In addition to these physical resources, practitioners of scientific computing also produce programs for performing simulation, data analyses, informative visualizations, as well as software libraries to make all these pieces work together efficiently. The defining characteristic of large-scale, complex scientific computing that has led to the need for specialized resources is the rate at which data is generated, processed, and consumed. The largest supercomputers today are able to perform millions of billions of operations per second, and even these machines are not fast enough to perform the kind of simulations that scientists can envision. In the near future, machines will exist that operate at exascale, that is, that are able to perform 1 billion billion, or 10 to the 18th, mathematical operations per second. This is roughly the raw computing power of the human brain, and this advance in performance is expected to help in producing ever better answers to more difficult questions, advancing human inquiry one more step. From the scale of a single laptop all the way up to exascale, scientific computing is a useful tool for researchers to have available. Like any tool, it is important to understand how it works and what it can do.